Hello. In this video, we will be going over 4 examples on how to use U-substitution on definite integrals. So, as a review, the procedure is that we are going to identify an inner function u and its derivative that appears in the integrand. Then we will substitute the function and its derivative. And for definite integrals, we then need to change the bounds, x equals a and x equals b, to be in terms of u by plugging those bounds into the substitution. Once we're now in an integral in terms of u, we can evaluate the full integral and find our answer. So we're going to go over 4 examples of this. So the first example, we know that the derivative of x squared plus 2x is 2x plus 2, which if I take 2x plus 2 and I multiply it by 5, that appears in my integral. So that tells me that's going to be our U-substitution. So u equals x squared plus 2x, du equals 2x plus 2 in parentheses, dx. And we can now substitute that into our integral. So x squared plus 2x is u. 10x plus 10 was 5 times 2x plus 2. So this whole thing is 5 times du. Also, 5 integral u to the 4th du. Step 3 is that we need to change the bounds. So our bounds are in x right now, and we change them by saying, hey, if x equals 0, that means u equals 0 squared plus 2 times 0, which is 0. And if x equals 1, u equals 1 squared plus 2 times 1, which is 3. So the bounds have changed from being from 0 to 1 to being 0 to 3. And now our integral in terms of x and our integral in terms of u are the same. They will find the same value. So when we evaluate the integral of 5 u to the 4th from 0 to 3, we will get this correct and same answer as if we were to evaluate the integral of x squared plus 2x to the 4th times 10x plus 10 from 0 to 1. So evaluating our u integral gives us 5 times, using the power rule, add 1 to the exponent and divide by the new exponent from 0 to 3, which is 3 to the 5th minus 0 to the 5th, and 3 to the 5th is 243. Next example. We want to identify that inner function. In this case, our inner function is going to be x squared because its derivative is 2x dx, and x dx appears in the integral. That also means that 1/2 du is x dx, telling us this x dx in the integral is going to be replaced with a 1/2 du. So making our substitution, we now have the integral of sine of u times 1/2 du, or 1/2 integral of sine of u du. We need to change our bounds, which is plugging in our bounds to the substitution. So when x equals 0, u equals 0 squared, which is just 0 again. Our lower bound continues to not change, but that's not always the case. And when x equals the square root of pi over 2, u equals the square root of pi over 2 squared, which is pi over 2. Now we have an integral we can evaluate. And the derivative of sine is cosine, so the antiderivative of sine is negative cosine. So we get that this is negative 1/2 cosine of u from 0 to pi over 2. Plugging in the bounds, we get negative 1/2 cosine of pi over 2 minus negative 1/2 sine or cosine of 0. Cosine of pi over 2 is 0, and cosine of 0 is 1. So this works out to be a positive 1/2. All right. Third example. In this example, we have a integrand that we could expand. We could just expand this out to be 1/3 to 1 integral of 4 minus a 12x plus 9x squared, which is perfectly workable, but then we would need to be plugging 1/3 into things with an exponent of 3 and can just get a little bit messy in the algebra at the end. But we could do that. We could work it. However, U-substitution could also be used here to keep the calculation just a little bit simpler. And sometimes expanding will be simpler, sometimes U-substitution will be simpler. I want to show how we could use U-substitution in this case. So what we will make u is that inside function, 2 minus 3x, and du is going to become negative 3 dx, or negative 1/3 du is dx. So making the substitution, we get u squared times negative 1/3 du. And when we change our bounds, when x equals 1/3, u equals 2 minus 3 times 1/3, or 2 minus 1, which is 1. And when x equals 1, u equals 2 minus 3 times 1, which is negative 1. And now work this integral in terms of u. The first thing is that when I'm multiplying by a negative into our integral, we can actually flip the bounds on the integrand. And we'd like to do that here because our integral has bounds of 1 to negative 1. The lower bound is larger than the upper bound. We could work this as it's written, but to keep track of negatives a little bit better, we're going to use this negative to flip the bound, turning this into the integral 1/3 of negative 1 to 1 u squared du. Now taking the integral, we get 1/3 times power rule, add 1 and divide by it. So 2 plus 1 is 3. So we have 1/3 u to the third, evaluated from -1 to 1. Multiplying 1/3 times 1/3, we get 1/9 u cubed from -1 to 1, or 1/9 1 cubed minus 1/9 -1 cubed. -1 cubed is -1, so we really have 1/9 plus 1/9, which is 2/9. And with this problem, we're able to use U-substitution to create bounds without fractions, making the evaluation at the end a little bit easier. All right, now our fourth example is this integral from 0 to 2 x cubed square root 16 minus x to the fourth dx. I'm going to take this inner function to be u, and knowing our derivative rules, the derivative of x to the fourth is 4x cubed. So that gives us a good indication we are taking this correctly because x cubed dx appears in our integral. So that x cubed dx is going to become a -1/4 du. And what's under the square root will become u. So we get the integral of the square root of u times -1/4 du. Now plugging in our bounds, we have that when x equals 0, u equals 16 minus 0 to the fourth, or 16. And when x equals 2, we have u equals 16 minus 2 to the fourth. 2 to the fourth is 16. 16 minus 16 is 0. I am going to use that same trick as before of there's a negative and my bounds have the lower bound bigger than the upper bound. So by removing this negative, I can flip the bounds to be from 0 to 16, and that integral stays the same. Now, the square root of u is the same as u to the 1/2. And now we can use that power rule of adding 1 to our exponent. So 1/2 plus 1 is 3/2, and dividing by our new exponent. 3/2, when we divide, becomes 2/3. So we have 2/3 u to the 3/2 from 0 to 16. 1/4 times 2/3 is 1/6. We have 16 to the 3/2 minus 0 to the 3/2, plugging in our bounds. And 16 to the 3/2 is 4 cubed. 0 to the 3/2 is 0. And 4 cubed is 16 times 4, or 64. So we have 64/6, which is the same as 32/3. So there were 4 examples on how we can use U-substitution to evaluate indefinite and definite integrals in this video.